friends, welcome to the channel Physics by IITians. In this video lecture, we shall learn about the electrostatic potential energy, the boundary conditions for the electric field, and we also learn and understand how to solve problems that has already come from previous year NET GATE papers. And in the earlier lectures, we have already covered conductors, dielectrics, the basic electric field, potential, all the things. So I request you to watch those videos before coming to this video. Okay, so let's start today's video. First we should know what is the meaning of electrostatic potential energy. Okay, I shall tell you first the definition, then I shall tell you the meaning of each term in this definition. So what is the meaning of electrostatic potential energy? So electrostatic potential energy is a potential energy and it results from conservative Coulomb forces and is associated with the configuration of a particular set of point charges within a defined system. So an object that may have electric potential energy by virtue of two key elements, one due to its electric charge and another due to its relative position to the other electrically charged objects. And don't confuse the term electric potential energy with the term electrostatic potential energy. Electric potential energy is used to describe the potential energy that is in a system which has the time varying electric field, and electrostatic potential energy is described to the potential energy in the system with time invariant electric field. So electrostatic potential energy means the electric field is not varying with time. Electric potential energy means the electric field is varying with time, like electromagnetic wave. So what is the summary of electrostatic energy? The work that is necessary to assemble a system of charges against Coulomb forces is stored in a system as potential energy, and this is known as electrostatic energy. So first we have already known the definition. Now we should understand that how to find out the potential energy of a discrete charge distribution. So suppose we are taking a final configuration of charges, that is discrete set of charges Qi, and they are placed at different Ri position. So we are proceeding to assemble this charge distribution as follows. Suppose the initially all the charges are at infinity, separated by infinite distance from each other. So the potential of the energy of the configuration is 0 because they are not exerting any kind of electric force to each other as they are separated the infinite distance. Now we what do we want? We will take the charges one by one, we will assemble and we will keep the charges to a finite distance with each other, and we will look into the amount of potential energy or amount of electrostatic potential energy. That is our aim. Okay, so let us take the first charge Q1 and bring it the position R1 from infinity. Now since we don't have, there is no charge earlier, so we don't have to do any work. Okay, fine. Now suppose we are taking second charge from infinity to a position R2. Since there is already present Q1 amount of charge, so that charge, that is Q1, will give or will exert some force, electrostatic force on this charge, second charge, that is Q2. And what will be that? That will be the due to the Coulomb's force. Okay, and the potential will be, that is on the charge Q2 due to the charge Q1 which is already present, that is 1 by 4 pi epsilon naught Q1 by R2 minus R1. So the work done in bringing the charge Q2 from infinity to the point, that is R2, will be Q2 into phi, and this phi, that is potential, is due to the charge Q1. So Q2 into phi will become 1 by 4 pi epsilon naught Q2 Q1 by R2 minus R1. Now suppose we are taking another charge, that is Q3, and it is placed at a point R3. Now we have to apply the superposition principle because the Q3 charge will experience forces due to Q2 and Q1, and these forces will not affect each other, okay, rather they will be added, and this is called the superposition principle. So the addition of this work done, that will be, that is 1 by 4 pi epsilon naught q3 q1 by r3 minus r1 plus 1 by 4 pi epsilon naught q3 q2 by r3 minus r2. So the new charge experience a force due to the superposition of fields that is established because of the two charges, one is q1 at r1 and another is q2 at r2. Similarly, for the I number of configuration, that is, or j number of charges, that is qj, and their positions are rj, we can write, that is, the work done, total work done we have to do, we have to take the summing over all this j, okay. So 1 by 4 pi epsilon naught qj, summing over all the charges qj. So 1 by 4 pi epsilon naught qj, sum of I qi divided by ri minus rj. Now look here, this qj is not equals to qi. Of course qi and qj will be different. Why? Because a charge cannot exert force on itself, or a charge cannot exert potential on itself. So we should avoid the term qi equals to qj. So thereby this term is only calculated when q1 and q2, or qi and qj, are different, okay. Now another thing you should also understand, that whenever you are counting the total work done, that is, you are counting, suppose I am taking charge 2 and I am taking charge 1, okay. So these two charges will give some potential energy. The charge 2 will exert potential energy to charge 1, and charge 1 will exert potential energy to charge 2, but both are equal, okay, the amount same. Now we should not count the same thing twice. If we just count the charge 2 is exerting a potential on charge 1, it is enough for us. So we should not double count the same factor. That's why this term, that was either earlier calculated the total energy work done as 1 by 4 pi epsilon naught qj sum of I qy by ri minus rj, it will be divided by a factor of 2, okay. So what will be the final expression is w equals to 1 by 2 sum of qy into phi, that is a function of ri, okay, where phi I is sum 1 by 4 pi epsilon naught qj divided by ri minus rj. Now earlier we have counted it for the discrete charge distribution, but our familiar world tell us that charges are continuous, which we are familiar with our familiar objects. So what will be the expression for the electrostatic energy, potential energy for the continuous charge distribution? So whenever you are taking the continuous charge distribution, this qi will become rho into dv, or it is rho into d3r or dq bar, and the sum over will be replaced by the integration sign. So the w will become 1 by 2 integration over rho, which is a function of r, phi function of r, dq bar, and here dq bar is dv, that is the volume element in 3 dimension. Now you can write rho, that is epsilon naught into del dot E, because del dot E equals to rho by epsilon naught. So write rho as epsilon naught into del dot E. What you will get? You get if minus epsilon naught by 2 integration over, here first understand it, epsilon naught by 2 integration over del dot E phi dq bar. Now E is equals to minus grad phi. So del dot or grad dot grad of phi minus grad phi. So it can be written as minus epsilon by 2 integration over phi r del square phi dq bar. Now here this term, that is del square phi, is present. Now we can simplify it by vector identity, and just simplify it, you will get one term, this is the first term, is will become 0, and this term will be remaining, and W will become only due to the second term, that is W equals to epsilon naught by 2 integration over all space E square dq bar. Okay, so here this is the final expression for the electrostatic potential energy. Why we have neglected, or why this term is 0? Because whenever you are considering a very large distances, this ds will be very large. Now at infinite distances, potential will be 0. Okay, so we can make this term as 0. Okay, so the W term, the remaining term is only the second term, that is epsilon naught by 2 grad phi square dq bar, or you can write it as E equals to minus grad phi, so it can be written as mod of E square dq bar. Okay, so this, now if this is the electrostatic potential energy, now if you want to take the energy density, what you have to do, you have to divide it by the volume. So W by V, that is the potential energy density, electrostatic potential energy density, that is UV, and it will become 1 by 2 epsilon naught into E square, because integration over dq bar will become volume of the system. Okay, so W by V, that is U, that is the electrostatic potential energy density, will become half epsilon naught E square, or half epsilon naught mod E square. So, or it can be written as, that is U equals to half integration E dot D dV, where D equals to, for the free space, D equals to epsilon naught E, and so U will become half epsilon naught E square. Okay, what will be the forces and torques for the electrostatic energy? So the force, we can write that work done, that is the force into displacement. So work done is dW, and that will be F dot dr. So dW equals to minus del du, so it can be written as minus grad u dot dr. So F will be minus grad u. And if the part of the system, suppose, is under consideration, is constrained to rotate about an axis, and it undergoes a small rotation due to the action of a torque, then we can write dW, that is tau dot d theta, and tau will become minus del u. Okay, so friends, we have our announcement that we have our full length test series are going on, the subject wise test series are going on, and the next subject wise test on the 10th October 2020, and the topic is electronics. And we also offer special interview guidance package for cracking integrated PhD physics, MTech examinations related to physics. Okay, so please, you can join this if you wish to clear any examination, any interview related to the PhD or integrated PhD physics. And the exclusive offer for the students who have already registered our test series, they will get this interview subscription with a reduced cost, that is 500 rupees per for the 1 year, and other participants can get 699 rupees for 1 year. So contact us on our Telegram channel, or you can call us. The contacts are provided in the description. Thank you. So the next topic is the electrostatic boundary condition, and in a video I have already discussed. So in this video I am not going to tell you, rather I shall give you the link. You can get it clicking on the I button of the right corner of your video, right top corner of the video. Okay, so what is the electrostatic boundary conditions? We should remember it, or we should understand it, that the normal component of the electric field has a discontinuity, and if there is existing a surface charge density, that is sigma. When there is a surface charge density is existing, suppose a conductor, in case of conductor, there is charges on the surface, but if the surface is made of dielectrics, then there is no free surface charge density. Okay, then this term will be 0. So this is the general formula, that is electric component, normal component of electric field has a discontinuity, and amount of discontinuity is sigma by epsilon naught. And if we consider the tangential component, the tangential component of electric field is 0. So the boundary, the tangential components of the electric field will be continuous, where the normal components of the electric field will be discontinuous. Let us take an example with the solving of problems. So the question is, at the interface between two dielectrics, that is one with the epsilon 1, another with the epsilon 2, that is dielectric constants, the electric field lines bend as shown in the figure. Assume that there are no free charges at the interface. The ratio of epsilon 1 and epsilon 2 is how much? So here it is mentioned that there is no free charge at the interface. So we can apply the boundary condition as d2 dot n cap equals to d1 dot n cap, because there is no sigma, and we know that d equals to epsilon e. So we can write d2 dot n cap equals to d2 cos theta 2 equals to d1 cos theta 1, and d2 equals to epsilon 2 e2. So epsilon 2 e2 cos theta 2 equals to epsilon 1 e1 cos theta 1. And the tangential component of the electric field is continuous. So e1 t equals to e2 t, and e2 sin theta 2 equals to e1 sin theta 2. Now there is a big question that student actually confused with what will be the tangential component and what will be the normal component. Don't worry, it is very much easy. First you should understand here which is what is the boundary. Here, look here, this is the boundary, okay? Because in here this is the upper boundary and this is the lower one, lower medium. So this is the boundary. So whenever you are taking the field component parallel to the boundary, that is the tangential component. Whenever you are taking the field component perpendicular to the boundary, okay, that is the perpendicular, means this one, that is the normal component. Okay, don't mug up, understand that whenever suppose this is the boundary, what will be the parallel component of electric field? Suppose this is the electric field is coming in, so the parallel component is this one. What will be the perpendicular component? Perpendicular component will be the perpendicular boundary, that is the normal component. And you just take those component which are parallel to the boundary, which are, and those component normal which are perpendicular to the boundary. Understand? I think you understand. I also have discussed it broadly in the video. Please watch that video, okay? And this is a homework for you. If you understand, you can surely do this. So the question has already come in GATE examination. So the question is a space between, sorry, uh, sorry for the interruption. The screen was just blackout. So the question is for your homework is the space between two plates of a capacitor carrying charges, that is plus Q and minus Q, and is filled with two different dielectric materials as shown in the figure. Now across the interface of the two dielectric materials, which one of the following statements is correct? E and D are continuous, E continuous, D discontinuous, D discontinuous, E discontinuous, E and D both are discontinuous. So this is the question, that is at this interface of this two dielectric medium, you have to answer in the comment.